It's supposed to also be 75. I don't like the way it 75. Yeah,
All right. Good morning, everybody. So a couple of procedural announcements. So reminder, midterm number 2 is going to be next Monday, a week from today. Practice exam will be posted up before the close of business today. I posted up a study guide, so that table of concepts and specific, things you should be able to do within each of those concepts last night. And I will be having a practice exam today, posted today, and then a review session on Friday evening. I don't have the specific time or location of that yet. I have to wait till I get confirmation from the facility scheduling people with the room. But that's where we stand. So keep an eye out for those topics, or for those things. In addition, I mentioned previously, right, that like the external convection material, there would be a practice homework associated with that. That's extra credit. I'll also be posting that this afternoon. I recommend that mostly as a study tool, right, for the upcoming exam. So the exam is going to cover essentially up through today's material. And today's going to be pretty quick and fairly straightforward. So lots of correlations. That's the thing to keep in mind for this exam. It's going to be convection, using some of the exact tools we've had, or the concepts on what convection is, local versus global heat transfer coefficients, and the equations of the governing equations, as well as correlations. How do you actually get down to calculating heat transfer rates when you don't have an exact solution available? More on that later. Last thing, the project. To avoid this kind of pile up next weekend, right? I did push the due date for the project back by one more week, so you guys have some extra room on that. Don't put it off to the last minute. The project's really not that hard. It's also It's relevant to this exam, so it's a good way to practice some of those external flow convection calculations as well. To date, right, we've been talking about. One more announcement here. So a couple, I guess, a number of lectures ago, right, when we were talking about dimensionless coefficients, this is something I should correct. I defined, right, this thing we see all the time, the Prandtl number, right, which is Cp mu over K, or mu over alpha. So, based on some rather obnoxious notation in the book, I mistakenly told you guys that this K should be for the solid. That might be the case for some very particular applications where you'd have the Prandtl number, but in reality, all of these should pertain to the fluid in convection calculations. So this is a fluid property, which is why you can look it up in tables in the back of the book. Okay, so I want to be clear that all quantities pertain to fluid. Okay, so today is going to be covering free convection. All right, so to date, as I said, we've been talking about convection only in one particular context. That is when you have some sort of flow that is being induced by a pump, a fan, or some external current. Okay, so those cases are, as we talked about in chapter 1, called forced convection. Free convection, on the other hand, so Okay, we'll say an externally induced flow is forced convection. Free convection, on the other hand, is a flow where, or is a situation where motion in the fluid, right, is induced by the heat transfer itself. We'll talk a little bit about the mechanism that causes that. But remember, convection is a combination of two things, right? Advection and conduction. And that advection term is the part that is attributed to the fluid motion, wherever that fluid motion is coming from. That's the transport of thermal energy or concentration or momentum. Okay? So that advection, again, externally supplied versus advection created by fluid motion due to free or natural convection. So to illustrate, what makes this work, what I'm talking about when I say, fluid motion that's induced by the heat transfer or due to the heat transfer itself. I'm going to consider a case of a house. So let's draw that's a pretty bad house. Looks kind of like mine. All right. So consider that this house, they decided to put their money instead of a new roof into some fancy schmancy heated flooring. Okay. Right. You'll see these in below tile floors and stuff in bathrooms and kitchens and foyers. So on a particularly cold day, you turn on this heated floor. You might expect, right, that if there's no air motion in the house, right, if everyone is holding very still, you'd expect that heat, right, the floor is going to be hotter than the ceiling. And so you're going to end up with some conductive heat transfer because the fluid, right, the air in the house is not moving. And so you're going to end up with this conductive heat transfer that creates a temperature gradient. So let's draw a quick sketch of what that temperature gradient might look like. So temperature on this axis. So we might have, right, the temperature at the floor, and up here the temperature at the ceiling, which is smaller. So we've got this gradient in temperature. Okay, and if we're talking about air here, right, we should know something about the relationship between temperature and density, okay, given to us in this case by the ideal gas law, which is going to say that P over rho is equal to RT. Okay. So this here indicates that if we're at constant pressure, right, atmospheric pressure, say this is at sea level or something, R is a constant, that T and rho vary inversely to one another. Yeah? So that would mean that this temperature gradient is simultaneously going to create a density gradient. That is, where the temperature is highest, the density is going to be lowest, and vice versa. Okay? So after this heater's been on for a while, what this means is, where the density is highest, that basically means it's the heaviest. Okay, so you've got a heavy gas or a heavy fluid on top, right? Denser air on top, less dense air on the bottom, which creates what's known as an unstable configuration. In the extreme case, think about, why do what happens to helium if you release helium at floor level, right? A less dense gas surrounded by a heavier gas, it moves up. This density variation creates a buoyancy force that wants to pull this less dense gas here up towards the ceiling, and in return force the denser gas down towards the floor. So you end up with this rising of light air and this downward circulation of heavy air. Okay. So this is what's known, this is a classic case of what's known as buoyancy-driven flow, where the temperature gradient actually creates this buoyancy that forces motion of the gas. So we're setting up, right? We've started out with a quiescent or a still fluid, and just due to that heating, that non-uniform heating, we end up with some sort of advection. And so we can imagine, right, there's this transport of hotter air, right, more thermal energy, away from the surface being replaced with cooler air. And so this sets up a case where we can see how we'd end up with this natural convection that is similar to, but maybe less effective than the forced convection we've been studying. So other examples. Oh, and I was going to show a really great video here in a second. Let me pull up. My internet is not. All right. You can see this very clearly in this technique known as schlieren visualization. So I'm not sure this is the same video that I saw before, but any of them should get the point across. Okay, we get to watch this whole advertisement. So schlieren visualization is a way using some mirrors and cameras to basically amplify the change in refractive index of gas, which is temperature dependent. So it's a way of essentially visualizing the flow of thermal energy in air. And so one of the things you'll see in this is that phenomena that generate heat, like the striking of this match, or even the hand that's holding this match, that higher thermal energy, those regions are going to tend to try to boil upward. Okay, this thermally induced buoyancy, which is very apparent right here. And what's less obvious, because it's not a strong temperature gradient, is that cooler fluid is rushing in to fill those voids left behind by the motion of the hotter fluid. So these are classic cases of buoyancy-driven flows. I'm not actually sure what we're looking at there. There are some other really good examples of if Google this schlieren visualization if you're interested in seeing some more examples. But there are some good ones of example, even those canned dusters that you'll use to blow out like computer keyboards, etc. Right, that expansion of that gas makes it colder than air. So there's a guy that takes a cup, blows his duster into it, right, fills it up with this cold fluid, and then he takes the cup in front of the schlieren and he dumps it out, and it's this pretty striking example of this dense gas pouring out essentially like you'd expect water to. All right. So, other examples are like these thermal plumes, which are those were examples of. Okay, this creation of this upward jet of gas driven by buoyancy is known as a thermal plume. It's not as obvious today, but usually you can see a similar thing at the top of the projection screen here, right? Created by the natural convective cooling at the top of the projector at the back of the room. So, all right, the governing equations for natural convection, you can see from those examples, right? It's a complex type of flow. This is not the kind of thing that lends itself to an easy analytical description. So we're not going to, but we're able to derive the governing equations. They're basically the same ones we've been working with. But for most cases, once again, a way of solving them exactly eludes us. So we're not going to even go down that road. We're going to jump straight into the more practical method of solving heat transfer problems involving natural convection, which deals with non-dimensional parameters and will lead to correlations. Okay. So, non-dimensional parameters are going to be important to us. We're going to take a little tour through these. The first one is a classic we know and love, the Reynolds number, which we're defining as U times L over nu. Okay. So, U in this case is our characteristic velocity. L is our characteristic length scale, and nu is our kinematic viscosity of the fluid. All right, so this begs a couple of questions. Right? What do we use for L? Newton, the viscosity is pretty obvious, right? You have something in a fluid, you use the kinematic viscosity of that fluid. But what do we use for L and what do we use for U? The whole premise, right, is that natural convection doesn't have some externally driven velocity to the flow. So that means we have to come up with sort of a scaling argument for what U is going to be and what L is going to be. Luckily, L we can answer by saying that this is going to be, once again, any linear dimension of the problem that is considered important to the case we're considering. So this is one you have to actually select from based on sort of intuition. If we're dealing with a plate, and we'll do this in an example in a second, if we're dealing with a plate that's 10 centimeters by 10 centimeters, in terms of its plan form, right? 10 centimeters. Use that as L. All right, so must be selected from linear dimensions of problem, and the saving grace here is that this will usually be obvious. Okay, I'm not going to make you hunt down or spend a lot of time pondering what to use for L. Usually, you'll be given one linear dimension that's dominant, and it'll be stressed to you that that's the one you should use, like the length and width of a plate. Okay. What about U? Well, the only velocities we have taking place in these cases of free convection, right, are those created by buoyancy. So if we went into this in greater depth and we used scaling arguments or a scaling analysis, we would find that U right, a representative or a kind of a rough estimate of that buoyancy-induced velocity is given by this expression here, where beta is known as the thermal expansion coefficient, and G is gravitational acceleration. All right, so now a little further into the rabbit hole. What is this beta? What is this thermal expansion coefficient? So beta is defined as -1 over rho times the rate of change of density with temperature. So for things that are considered, right, for most objects, solids, liquids, most objects that are not gases, this will be tabulated in those thermophysical properties that are at the back of the book. Right? For gases, we have the ideal gas law working for us, which means that for an ideal gas, beta is equal to 1 over rho. The temperature of P over RT, which is going to be equal to simply 1 over T. So the idea is the thermal expansion coefficient is a representation of how much is the volumetric, how much is a volume of a given unit of mass of this particular fluid going to grow per change in temperature, where this T should be an absolute temperature. So don't use Celsius here. This has to be populated with Kelvin. Okay. And as a reminder, so you have it in the notes, if not an ideal gas, beta tabulated with other thermophysical properties. Okay. So if we plugged this into, right, so we have, based on beta, we have an expression for U, and we plug that expression for U into our expression for the Reynolds number. We're going to end up with the Reynolds number written out as G beta, Ts minus T infinity L times L all over nu. And if we squared this, Reynolds number squared, beta Ts minus T infinity times L cubed nu squared. We're going to define this particular case, right? This is a very specific Reynolds number. We're defining the Reynolds number based on the characteristic velocity created by buoyancy. So this particular case of a buoyancy relevant Reynolds number squared, we give a special number, special notation known as GR, which is the Grashov number. And you can love it or you can hate it. In fact, they keep giving different names to subtle variations on the same thing. But I want to be clear, right? The Grashov number is a Reynolds number squared, right? There are a million different versions of the Reynolds number. So this is the square of the Reynolds number, entirely specific to buoyancy-driven flows. And finally, a last one. So let me go ahead and star this. Have that one written down. And finally, the last one is known as RA, which is a product of the Grashov number and the Prandtl number. And we know as the Rayleigh number. And so written out, this becomes beta ts minus t infinity L cubed over alpha. So the Rayleigh number is now, right, if the Grashov number is a version of the Reynolds number squared, the Rayleigh number is basically, it contains the information of the Reynolds number and the Prandtl number, which means it's got some information about the relative balance between inertial and viscous, or buoyancy and viscous forces, combined with information about the thermal versus viscous diffusion. So what that means is that the Rayleigh number for natural convection or buoyancy-driven flows, the Rayleigh number here is what tells us whether a flow is going to be laminar or turbulent. So for Rayleigh number less than 10 to the 9th, approximately, we say that the flow is going to be laminar, and Rayleigh number less than greater than about 10 to the 9th, we're dealing with turbulence. So what's nice about this, right, is even though this is a lot more complicated of an expression than like the Reynolds number for flow over a flat plate, it's still very easily computed once you know what kind of fluid you're working with and you have some idea of the length scale that this natural convection is occurring on. Okay. So the idea here is for natural convection, right, where we have these buoyancy-driven flows, we're going to be seeking, as always, H, right? That convective heat transfer coefficient, which is non-dimensionalized as the Nusselt number based on length. So Nusselt number equal to HL over K, which is going to be a function of the Rayleigh number and the Prandtl number. Okay, so we have the Reynolds number and the Grashov number and the Prandtl number actually wrapped up in the Rayleigh number. Okay, so that contains a bunch of that. But then there's a separate explicit dependence on the Prandtl number. So, as always, this is a empirical result. Okay, the correlations that give us approximations of this function are due to experimental data and simulations, and generally not come up with by crunching through the numbers by hand, right? So these correlations are compiled in table 9.2. So you're going to want to get familiar with that table, and so this will be right. You'll get a chance to do that on the homework. But a last note before we dive into an example and show how the rubber meets the road here is that all fluid properties evaluated at, once again, we're defining this film temperature, T sub F, which is equal to the average of the surface temperature and the temperature far away from the surface. And so, once again, you know the temperature of whatever is being convectively heated or cooled. You know the fluid temperature, the average. Get TF. Look up your thermophysical properties of your fluid. Figure out what your length is. Then you can calculate the Rayleigh number and the Reynolds number. Find Nusselt number and get H out of that, and you're home free. Okay, so as an example, and this example is going to be a little bit more in depth, but hopefully we'll find that it's none too difficult. So consider a case where we've got an aluminum alloy plate with the following properties. Well, it's at a surface temperature of 227 degrees Celsius or 500 Kelvin. At those temperatures, it has a density of 2770 kilogram per meter cubed and a specific heat capacity of 983 joules per kilogram Kelvin. All right. So this plate here has been has dimensions of 0.3 meters by 0.3 meters by 15 millimeters thick. Okay, so here's the edge. And so it's been heated up to this 227 degrees Celsius. And then it's being just suspended vertically in a room of still air. So it's being placed into a room with a temperature of T infinity equal to 27 degrees Celsius, which is equal to 300 Kelvin. Additionally, right, we're going to bring, just so you don't forget that it exists, we're going to bring radiation into the mix here and say, right, that the boundaries of this room far away can be treated as a black body. It's probe error. Can be treated as a black body with temperatures of also 27 degrees Celsius, 500 Kelvin. And finally, we're going to say that the surface of this plate here has an emissivity of 0.25. Okay, so to kind of get a handle on this problem, right? We have all our properties for our plate. We are assuming, right, we specify the emissivity. It's basically we've got a metallic body sitting surrounded by some faraway surroundings. These surroundings we're going to treat as a black body, and this plate we're going to treat as a gray surface. Now, just a reminder, we haven't really gotten that deep into what makes a gray surface and what makes a black body, but from chapter 1, this is the particular situation where we have an easy equation, the easy version of the rate equation, right? A gray surface surrounded by a large black body, right? So you're safe to assume that in any radiation case we encounter for right now. So what we're asked to find here first, an expression for dt yeah, we'll just say a symbolic expression, and then the value of dt at right, the instant shown in the sketch. And for both of these cases, right, we're going to assume that the temperature of plate is uniform. In other words, that the BO number is significantly smaller than 0.1, which means we could apply a lumped capacitance analysis. So this problem actually has a bunch of things rolled up into it. It's got radiation, it's got this new mechanism of natural convection, and we've got transient heat conduction, or transient heat transfer. So, to kick things off, as always, with problems that involve multiple mechanisms of heat transfer, I recommend drawing a energy balance, a control volume. This one's going to be pretty simple. Say here's our plate, the edge of our plate. Go ahead and surround that with a control volume. And basically what we've got going on is there's going to be Q due to convection, and there's going to be Q due to radiation, both leaving. We're going to go ahead and assume that all of the heat transfer is going outward in this case. Remember, radiation is actually made up of some heat transfer in, some radiation coming in, and some going out. But we're going to go ahead and assume that the net radiative heat transfer is outward because the body is significantly hotter than the black body surrounding it. So our energy balance would be written as E dot stored is equal to E dot in minus E dot out plus E dot gen. Okay, we've got no heat generation. In this case, we're going to say we've got no net heat transfer in. So what we've got is essentially E dot stored is equal to negative Q convection minus Q radiation. All right. So, as in lumped capacitance analysis, right? What we're going to go ahead and do is say that E stored is equal to, right, rho volume Cp times T, right? The density times the volume, so the mass times the thermal heat capacity times the absolute temperature of the aluminum plate. Okay, so we're going to say that Q convection is equal to the surface area times H times Ts minus T infinity, and say Q radiation is equal to AS times epsilon times sigma times Ts T infinity all to the fourth. And because we're assuming that, right, that the temperature of the plate is uniform, basically the temperature at the surface is the same as the temperature at the middle of it, T over here in this expression, we can go ahead and call that Ts because it's all the same. So now we're working with everything in terms of Ts. So plugging these in then, what we get is rho v Cp times dTs dt. Okay, so there's our time rate of change of stored energy is equal to As times H Ts minus T infinity plus epsilon sigma Ts to the fourth minus T infinity, or sorry, that should be T surroundings, which is the same as T infinity in this case, but to be correct. All right, so right for part A of the problem, we're just looking to isolate this, come up with a symbolic expression for T, the time rate of change of the temperature of the plate. So that's pretty easy. We can just divide through by rho v Cp. We're going to end up with dTs dt is equal to negative surface area over rho volume Cp times H Ts minus T infinity plus epsilon sigma Ts to the fourth minus T surroundings to the fourth. And we could go ahead and leave it at that for the solution to part A. All right. So part B is, what's the actual number that we get for this? Which means we have to find a couple of quantities. Right? We're given rho and Cp. The volume we can calculate from the dimensions of the plate that we're given. Surface area of the plate we can calculate from the dimensions given. We know Ts, we know T infinity, we know epsilon, right? That or 0.25 is for the emissivity. Sigma here, if you don't remember, this is the Stefan-Boltzmann constant, which is just a constant number. It's at 5.7 times 10 to the negative 8. Ts we know, T surroundings we know. So the only thing here that we don't know is our H. Okay. So once again, boils down to that convection. So for part B, we need H. I should mention here that, right, H. Am I talking about, notice that there's no subscript X and there's no bar over the top. Are we talking about a local convection coefficient, or are we talking about a average convection coefficient? Just based on, I heard an average. That's a good intuition, right? Why would that be? The whole plate, right? We're considering the net heat loss from the entire plate. We're not putting a temperature probe on it and just trying to figure out the heat loss from one particular location. So if in doubt, kind of zoom out and look at the problem and say, am I considering heat loss from the entirety of an object? If so, we're dealing with average convection coefficients, right? It's very specific times when you'll be looking for local convection coefficients, and I'll try to make that clear when we're doing that. So the H we're looking for here is really H bar. So to do so, we need to define the thermophysical properties of the fluid. So Tf is going to be, right, 500 Kelvin plus 200 Kelvin over 2, which gets us 400 Kelvin. From table A4, air at 400 Kelvin has a viscosity of 2.6 times 10 to the negative fifth meters squared per second, a density of 0.871 kilograms per meter cubed, a conductivity of 0.0338 watts per meter Kelvin, a thermal expansion coefficient, right? It's not listed in table A4, but air can be treated as an ideal gas. So we're going to end up with 1 over T, which is 1 over 400 Kelvin.
Did you just round up 400?
Huh?
Did you just round up 400?
Did I just round up? Oh, sorry. 500. This should be 300. My bad. 300 Kelvin there. Sorry. I can do maths. And sorry, I was thinking there's a temperature jump of 200 Kelvin between the surface and the air. That was my mistake. A thermal diffusivity of 0.0. No, that's not quite right. That's going to be 3.83 times 10 to the negative fifth meters squared per second, and a Prandtl number of 0.69. So, taking these numbers, first step is to calculate the Rayleigh number. And if we plugged these numbers into, the expression for Rayleigh number, which is going to be G beta Ts minus T infinity L cubed over nu times alpha, right, we would get a value of 1.309 times 10 to the 8th. I should mention here that, in case you didn't pick up on that, L here, L is equal to 0.3 meters, which is the width and height of the plate. Okay. So we're going to run out of time here. We only got like 2 more steps left, but I'll just close off by saying, right, we've got a value of the Rayleigh number. We said that the differentiation between laminar and turbulent flow for buoyancy-driven flows is 10 to the 9th. We're less than that, so we're going to be looking for a Nusselt number correlation in laminar flow for a vertical plate. Okay, and those 2 facts are what are going to direct us to the equation that we're using for the Nusselt number. So we'll do those last couple of steps on Wednesday. Congratulations on sticking that out. That's most of chapter 9 right there. We made it through. It's a pretty short chapter. And yeah, we'll see you guys on Wednesday.